All right. Hello, everyone. Welcome to the second part of the PCB workshop series that we're hosting. If you weren't able to make it to the first one, that's absolutely fine. We really were just getting people's licenses and downloading set up last time. I'm going to go over briefly some of the previous stuff we did last time to get the people caught up. And then we're just going to go ahead and get started. Today, our goal is to try to at least start a PCB, a breakout board for a IMU sensor. And a breakout board is essentially just a small PCB that has, like, for example, a sensor on it that we can interact with like a Arduino or something like that. So it's just a board with a sensor on it, and then we can have power and communication to that board. So it can be placed anywhere, really. So the sensor that we are choosing to do today is called the MPU 6050. This is a IMU, or an inertial measurement unit sensor. Essentially, what it does is it has a gyroscope in it, so it knows which direction it's facing. It has a accelerometer in it, so it can detect how much acceleration is happening. And it also has a magnetometer in it to detect the gravity of the Earth and actually be able to kind of know which way is north and stuff like that. So it's an extremely useful sensor. It's in every single one of your phones. It's all over the place. You'll see it in the rocketry clubs. You'll see it in, I don't know, the Lunabotics. But the reason that I chose it is because we're using it in Micromouse, which is another club organization that IEEE has, where it's a small robotic mouse or little small robot that solves a maze autonomously. And you can see right here is the sensor. So that can give us information about how far the mouse is turning. So if we need to do a 90-degree angle so it can turn to different parts of the maze, it knows exactly when to stop at 90 degrees. And it also can be used for measuring rough movements with the accelerometer in there. So to get started, first things first, we're going to go back for the people that weren't able to make it on Wednesday. I posted a link in the Discord. And in the Discord in general, I posted a link to the footprint files. I misspelled files, but if you go to the Discord, you can find this link right here that will give you, bring you to this page. And just to give a brief overview for those who missed it, footprints are essentially how the software views a specific component. So for example, a footprint for a schematic footprint for an LED would look like this. So you might have seen this in your classes, or a resistor. This just is a box right here, but it's essentially what it looks like on the schematic. And the PCB footprint is going to be what that actually looks like on the PCB. So for example, an LED would look like this on the PCB, and that's the PCB footprint. So again, you can look down here, and inside the file, you can see that there is a 3D footprint. So this is like a 3D model, so you can see what it looks like. And then this is the PCB footprint. So it knows how to print that footprint onto the PCB when you do get there. So there's a really useful library that I found from Phil's lab, who also does a bunch of YouTube videos. If you go to that link in the Discord and go right here to code, you can download the zip file. And this just has a schematic and PCB footprints for a lot of the components we're going to be using in today's lecture. So it might take a second, but once those are downloaded, take a second. And also, if you guys ever get behind or anything like that, just raise your hand, and Kevin and Darian will be here to walk around and help you guys out. So once it's downloaded, you can simply extract those, and you can put them anywhere, but I'm just going to put them back into my downloads. And then in here, you can see that there is two files called the schematic and PCB files right here. Um, so now that that's downloaded, hopefully you guys have that by now. Um, I'm gonna go back and create a brand new project. So for those of you who missed the lecture on Wednesday, to create a new project, we're gonna go to File, New, and we're gonna hit Project there. And I'll give you guys a second to catch up right here as well. So, if you, yeah.
Is it okay if is there any way if you could ask the libraries, the project while you were creating a new one? Or create or then you could add the library there?
You can create it and then add the library later. It doesn't really matter. If you create it, the libraries aren't there until you import them in. So when you create it, there's no libraries kind of in there. And for those of you that were there last week and already have a project, you could just use the same one.
Like the actual wall. Oh, no. Thank you for your.
All right, so hopefully by now you can follow along. If you're still a little bit behind, no worries. Darian and Kevin will gladly walk around if you just raise your hand and help you out. But again, to create a new project, you go to File, and then it's going to be Add New, and then you can choose Project from there. Um, I guess I'll redo that real quick. File, New, and Project, and I'm just going to call this PCB Workshop 2 MPU 6050, but you guys can name it whatever you want. So I'm going to create this new project. Now, once this project is here, you can see in my case, it opened up at the bottom. And right here, this is the new project. So I can go ahead and we're going to add a couple things because right now it's completely empty. So you need to add a schematic file and a PCB file so you can actually start working on it. So first, you're going to find the file that you're working on, right click it, and go to Add New to Project and do Schematic. All right, give it a second. And this will go ahead, you'll see it adds down right there, and then you'll have this big empty schematic sheet. Next, what you want to do is go ahead and add new to project, and you could do PCB. There we are. So now we have these new two files in. And then next, I'm going to go ahead and add the two files that we just recently downloaded. So you can right click this as well and add existing to project. So I'm going to give you guys a second to catch up, and then I'm going to go ahead and continue. Again, to add something new to the project, just right click it and do add new to project. And then we want a schematic file and a PCB file. Oh, yeah.
Kind of name, you keep it just like, so like, you put sheet workshop, like, or.
Yeah, so eventually when you do save it, so for example, I'm just gonna hit, you can hit the save button here, or you can do Control S, and it'll ask you to name it. So the first time you save it, it's gonna go and ask you a name. I'm just gonna do, I like just doing SCH for schematic, and then I'm just gonna do, oops. Yeah, but when you save it, that will come up, so you can name it whatever at that point.
No, that's what you keep those name structure, when you. You're
Oh.
shipping off.
So yeah, that's later on. The job files and stuff, it has a specific name, but those, you know, you don't need to worry about that yet. All right. So by now, hopefully you have those files that we downloaded before, and you can add existing to project. And I'm gonna go to my downloads because that's where I personally unzipped the files. And you can see right here, here's the files that we unzipped. And I'm just gonna go click that one and then control click to choose both, or you can go through that same process twice, but you can just choose those two and open them. And now you can see that we have a schematic footprint library and a PCB footprint library. You can confirm you have those now by going to the panels in the bottom right corner. The panels right here is where you're going to have all your component choices. You can open and close your project on the side. So for example, if I close that, it's just that. Your panels is where everything is going to be on Altium. So to confirm that you got those libraries imported, I'm going to go ahead and go to components. And components are going to be all the components that are already downloaded in Altium or on your computer. There's a ton of different components, but in this case, we are looking for the Phil's Lab one. And it's loading, but you'll know it's there because if you click down on the all, you can see the Phil's Lab. I have some extra ones here, don't worry about that. But if you don't see the Phil's Lab one right there, then you haven't properly kind of imported the libraries, and you can go ahead and raise your hand and have Kevin and Darian help you out there. All right. So now that we have those files imported, I'm going to choose pretty much most of the components that we're going to have today are coming out of here. However, to teach you guys how to use another form of finding components, if you go to the bottom right panels right now, the components, again, are all the things downloaded on your computer or on Altium. However, Altium also has a manufacturer part search that will allow you to search the internet for parts and models that they have ready for you. So I'm going to go to the manufacturer part search. And in this case, I'm going to look up, oops. I'm going to look up MPU 6050. That is the sensor we're going to use today. Again, down in the panels, you can go to manufacturer part search. That will bring this up. I personally dragged mine out, but I think yours will probably start off to the side like this. But I like to have mine in the middle, so I just kind of dragged it out. So once you get here, just go type in MPU 6050 and hit enter. And this is the exact sensor that we're going to be using. And there's a couple things that you want to make sure before you choose this part. So first of all, this little line right here that's orange is just letting me know that it's not recommended for new design because it's not in production anymore. If it's green, then it's still in production. If it's orange, then it's not. If it's gray, it doesn't know. The next thing, which is a lot more important, is this. It says has models. If this little circuit bug thing right here is green, then you know that it has models and you can actually drag them in and it will automatically import the schematic footprint that we were talking about, the PCB footprint that we were talking about, and the 3D model. So you can actually confirm that if you go down and scroll down there. Right there is the schematic footprint, and there is the PCB footprint, and that is the 3D model. So Luckily for us, the sensor that we're using is in the manufacturer part search, and we can go ahead and find it here. There's a couple different ways you can find parts if you can't find them in the manufacturer part search. A couple options is using Snap EDA, which is a website that has a bunch of models that you can reference to. We went over that a little bit last week. In addition to that, DigiKey actually also has a lot of models on their website. So oftentimes if you see like it says CAD or EDA models, then you can actually grab those files and bring them into Altium to use. And I'll go over a little bit more in a second. So next, once you find this part here, you can either right click it and hit place, or I just click it and just drag it in. Both work. If it's not dragging in, you can right click that and then click place, and it does the same thing. All right. So by now, hopefully you guys have figured out how to put the MPU 6050 figure onto your schematic. So now, how do we build it? How do we know what to place? There's a bunch of pins here, what of all of them do? Who knows? That's why we have data sheets. Data sheets are your best friend in PCB design. You will be referencing them countlessly. I can't stress that enough. Data sheets are incredibly important to sit down and actually try to read through some of it and understand it. So, how do we find a data sheet? Oftentimes you could find them on the internet if you look up the exact name, but me personally, I like, you can double click on the component and it'll bring up the properties. If you dragged it from the manufacturer part search, it actually has this thing on the very bottom where it says the part choices, and it'll actually give you links to websites to buy them and also for the data sheets. So for example, I double clicked this and opened up the properties tab and then scrolled all the way down to the bottom. So it starts off like this. I scrolled all the way down to the bottom and it gives you a link to the actual part right there. So if I go ahead and click this link to DigiKey's website, it'll load up this. And then here is our part right here. And we can order it right through DigiKey just like that. And what I was talking about before with the CAD models, you can see it has EDA and CAD models. So if I click this here, if the models for whatever reason aren't in Altium, you can find them right here on DigiKey. And you can see here's the schematic footprint and the PCB footprint. Oops. So DigiKey makes it really easy for you guys to get the data sheets the data sheets and all the information right from there. All right, so now that we found the part on DigiKey, again, if you weren't able to find that link, you could always just click to the side and go to get DigiKey's website and just type in the part number. So in this case, it's an MPU 6050. And right here, here's the component. Now, we're back to this page and we're gonna go into the data sheet. DigiKey provides the data sheet right here, so we can go ahead and click that. And now we are bombarded with too much information. There's like probably 50 pages on here. It's really hard to follow a lot of this. As the more you get used to going through these data sheets, the less scary they are. However, I understand at first it's a little bit hard to know where to even start on something like this. However, I'm just gonna kind of skip a lot of the data sheeting today because we're planning on going over that next time. And if you scroll down, I believe it's page 20 or so. Here it is, page 22. On page 22, it has a typical operating circuit. Oftentimes for chips and sensors, the manufacturer will put a typical operating circuit in their data sheet, so it does a lot of the hard work of choosing components for you. So you can see here, we're working with the MPU 6050, not the MPU 6000. And so right here, it shows us a typical operating circuit. And we have, it looks like some capacitors on these pins. These pins would be ground, power pins. SDA and SCL are I squared C communication lines. So these are the two lines that will actually be talking to the microcontroller to tell it, how far it's turned, how much it's accelerating. These are the two communication lines right there. The rest of the stuff, in all honesty, you're probably just going to have to go to the data sheet and start reading to figure out if you need it or not. But we're not focusing on that today. We're focused on PCB design. And so we're going to go ahead and just go straight to Altium and start adding some of these components that we need. So you can see here, it's kind of showing us what components we need as well. I'm just going to start from the bottom left right here, and we're going to need a 10 nanofarad capacitor. All right. If we go back to Altium, and I'm going to now use the components tab in panels. So again, once you're back in Altium, you can hit panels and components. And in the components, you can choose the Phil's Lab library that we've just added, and you can look up CAP. So this is where you're going to find your basic capacitor footprints. So you might say, okay, well, how do I know if it's 10 microfarad, 1 microfarad, 10 nanofarads, or all this information? But in reality, most of the time for capacitors, at least for the smaller ones, it doesn't really matter the exact size of the capacitor, but rather the footprint of the capacitor. So if you go ahead and look at the DigiKey ruler that was provided to everyone that you guys get to keep now, you can see on the front of it, or the one with the centimeters on it, on the bottom left, you can see where kind of the dots are going down. Right there, you can see all these different numbers like 2512, 1206, 0805, 0603, and these like kind of rectangles that get progressively smaller. So it's in the bottom left corner on the kind of centimeter side. Yeah, so it's kind of right below all those letters like the A, B, C, D, E, F that are going down, but it's going to be right there. I guess I can maybe put it on the camera, but so if you guys see that in the bottom where it says 2512, actually I can bring it up on the camera, might as well. So you can see right in the bottom corner right there, those little rectangles right there. And that's right there. And then I know it's in reverse, so you guys can't really read it, but it says like 2512, 1206, 0805. And those are your different sizes or footprints of your basic passive parts like capacitors and resistors. So you can see right here, we have those exact numbers next to the caps. So for example, a cap 0805, if you go to look at your ruler, you can see the 0805 points to two small little ones right there. You see the two 0805 is like the third one down, I think. So that's that size. That's how small that is. And then obviously it gets progressively smaller to the point where it's like a grain of sand. In our case, we're going to be wanting to use 0603 capacitor and resistor sizes. And you can see again there, 0603 is extremely small. But having smaller capacitors and resistors means that you can fit things on the board a little bit nicer. And it also means that you can have your entire product be a little bit smaller as well. So 0603 is kind of a nice in-between to where you still have to use tweezers to put it on, but it's not like the very bottom one where it's just like kind of impossible to solder. For these, you would likely use something like a hot plate or a hot air gun to solder. You would not be using an iron like traditionally. In the soldering workshop, hopefully we can do mostly through-hole soldering, which you probably are more familiar with, and then we'll throw a couple SMD parts so you can actually solder some of those smaller ones on there in the workshop. And that's going to be coming up in like 2 weeks, I believe. All right, so we're going to choose the 0603 package, and we're going to go ahead and move them on. And I believe there's 4 capacitors. So I'm just going to, copy. Oh, whoops. I'm just gonna copy the one that I moved on 4 times. All right. So now we need to go ahead and place these where the data sheet was recommending. So if we go back to the data sheet, we can see, for example, in the bottom left one, we have on pin 8, there is a 10 nanofarad capacitor. So let's go back to here, find pin 8, which is right here in the bottom right. Go ahead and I'm just going to place that right here. And then to go ahead and connect this capacitor, you can go up here, and here's where you can place the wires to actually connect them. You can click that, and I'm going to click on 8 and just move it over there. I'm going to delete that. And I'm going to show you one other way that you can do it. If you don't want to go up there and click the wire every single time, you can also click Control W on your keyboard and pull up the same exact thing. So now I can just click that, and then when you're done, ready to placing wires, you can hit Escape. And then you can go back to just your normal operations. All right, so this capacitor was a 10 nanofarad capacitor that goes to ground. All right, I'm going to put a ground symbol right here. So if you look at the top, there's a couple things right there. So you can right click and you can see there's a ground pad, power, all these things. But right now I just clicked on the ground pad and it creates one here and I could place it there. I'm going to give you guys a minute or two to catch up and have Darian and Kevin walk around to help you out. I'm just going to briefly go over what I just did one more time though. So I went into panels, components, which shows the 0603. Go ahead and drag that down here. Oh, one more thing that I forgot to mention, everyone. The way that I turned the capacitors, because they start sideways, I completely forgot to mention that. Sorry about that. If you click on it, you can drag it around. And if you click space bar, you can switch it. So sorry about that. I forgot to mention. Space bar is how you flip the capacitor to be any way. Now, if for whatever reason you want to mirror it, so because like for example, if I flip this, it's upside down, but what if I want these pins over here, but it be that way? If you double click and go into the properties and scroll down again, you can click this and it'll mirror it. So you don't, that way you can mirror it or just flip it. So yeah, but I'm just gonna go back there and go back to there. And I know you guys came late, so you're a little bit behind, but Kevin and Darian should be walking around. They're helping out other people, but you can just raise your hand and then they can come up and help you out. Okay, yeah. Oh, okay, perfect. Oh, nice. So you're a little bit up to date. Cool. Perfect. Hey, you guys want some stickers? Did you see stickers like that? How about you? What was that? Oh, the bus was delayed? Oh, dude, yeah, I thought, I know, the bus is, dude, the bus is either like leaving the second it should be, or it's like 30 minutes late. So it's like, what do you do? You know?
Was late today, like 20 minutes late.
Yeah, that's ridiculous. Yeah, but no worries. Yeah. Oh, go through the SSO. If you open it, you have Altium open when you're configured. So go.
Oh, yeah.
Is that from?
Oh, man.
Yeah. So someone, two other people are having the same exact issue. We don't know what's happening. We're trying to figure out with them because we haven't been able to log in yet. And how many emails did you get from Austin? Yeah. Yeah, but. Yeah. Yeah, because, yeah, you should have gotten another email from Altium as well. But it's, yeah, that's the same issue we're having. We don't know. They don't know what's happening. Yeah, yeah. But yeah.
It's a valid.
Your school, you're calling me. All right. So I'm gonna go ahead and continue here. So I'm just gonna kind of redo what I did really quickly. I went into the panels, components. We chose the 0603 capacitor. Press spacebar to flip it around. Again, from the data sheet, we know that pin 8 has a 10 nanofarad capacitor. So pin 8 is right here, and I press Control Y, Control W to create a wire, or you can go up here and just click this to create a wire. Both work. I like doing Control W. And then I'm gonna go ahead and connect that there. And then lastly, I went up right next to the wire. You can see that there's a ground port. I clicked this, went down to the bottom, and placed a ground port right there. So we have made this first connection right here. However, you can see there's also another thing that's connected to it saying V logic. In this case, the V logic is just going to be the voltage coming in. That's just the logic level. You could sit down and read the data sheet to figure that out, or you can just listen to this for now since it's going to take too long. So I'm going to go ahead and right click the ground button right there, and then it has a drop down for a bunch of different ports that we can place. I want to place a power symbol, so I'm going to go ahead and click this, and I'm just going to place it right there in the corner. Good practice is to put power symbols and power things pointing upwards and any sort of ground pointing downwards. So you don't want to, for example, place a power like this, like upside down, or a ground upright, or upside down like that. You don't want to, this is bad practice. It's good practice to always have your ground pointing down and your VCC pointing up, or your power. However, just to know what the power is, we don't want it to say VCC. We want a very specific voltage. It's going to be 3.3 volts. And so I'm going to double click the symbol right there, and that's going to open up the properties tab. And then right here under name. So name is, again, if you double click this, it opens the properties tab up, and you can go ahead and change the name. I'm going to change the name to plus 3V3, and that just stands for plus, so it's above 0, 3.3 volts. So now we have pin 8 figured out. You can see below here, 8 has a capacitor to ground, and then we have V logic, which was 3.3 volts in our case. The next one we have is pin 10. We have a 0.1 microfarad capacitor going to ground. So on this, I see pin 10 is right there, right below it. And I'm just gonna, I'm gonna go ahead and move this, I'm gonna give it a little bit more space. Maybe I'm gonna move this whole thing over. So you can always drag things and choose multiple. If it's green, If it's just barely touching it, it will still select it. However, if you drag it the other way and it's blue, it will only select everything that was inside of it. So, for example, if I do this, it's only selecting the ground, the capacitor, and the symbol for power. But if I do green, so if I drag up this way, you can see it selects the wire and pretty much anything it touches. So in this case, I'm just gonna, oops, I'm just gonna select this and move everything over a bit just to give us a little bit more space. And then I'm just also going to use a wire right there. And again, I'm just doing Control W to create a wire. All right. So, and while we're at it, I've kind of forgot before to label them. So this was a 10 nanofarad capacitor going to pin 8. So I'm just going to go and double click this to open the properties up. And I'm going to say 10 NF. So again, I just double clicked the capacitor, opened it up, and then changed the value from C0603 to 10 nanofarad. Now I know that this is a 10 nanofarad capacitor right here. The same goes for the other one. The other one was a 0.1 microfarad capacitor that was going to pin 10. So pin 10 is right here, and here's our capacitor. And it was a, oops, yeah, it was a 0.1 microfarad. All right. Next, if you do, if you see here, there's the ground pin right here. Since we already have a ground right here, I'm just going to connect that to it. So now the ground pin right here is connected as well. Um, now, now I'm going to go to the next capacitor that we have here that's on pin 13. So let me go back to here. And again, right before I just added a quick wire right here to connect the ground to ground. And the next one was pin 13. We have a 0.1 microfarad capacitor. So I'm just going to add a capacitor right there. Pin 13 is right there. Again, I'm just doing Control W to choose the wire. And I'm going to go ahead and connect that there. You can see on the data sheet, it's saying that this capacitor is going to ground. So I can go ahead and use another ground symbol right there and place it on the same ground. And they do not need to be physically connected. If they're the same name, they are connected. So grounds are all connected to one another. So you don't need to make all the wires go to that one single ground. That would be a little bit messy. So in addition to that capacitor, it was a 0.01 microfarad capacitor. There's also a VDD power symbol right here. So we also need to connect that to power. So first, I'm just going to go ahead and change the value to 0.1 microfarad, just so we know what that is. And then next, I'm going to add a power symbol again. But instead of going up here and choosing the same power symbol, I know that our power coming in is 3.3 volts. So I can just simply click this same one back here and Control C to copy it. You can also right click it and copy the part and right click again and paste the part or Control V. And then I'm just going to place it right there. And now we have our 3.3 volts coming into our VDD. And we can see here pin 13 is going to that, and we have that capacitor done as well. So next thing we want to do is add the last capacitor. We already put the ground right here. The same pin 18 goes to ground, but we already did that before. 18 is already going to ground. So from the data sheet now, we can see on pin 20, we have another capacitor to ground. All right, so if we find here, we have pin 20 right here. We're going to need another capacitor to ground. So, whoops. And if I mess up, I'm just doing Control Z to go back. similar to anything else. So I'm going to click this component and drag it over right there. Pin 20, I'm doing Control W to choose wire. And this goes to ground. So I just went and added the last one that went to pin 20, and I believe it was a 2.2 nanofarad capacitor. Sorry, let me go back. It's a 2.2 nanofarad capacitor. So I'm going to double click that and do 2.2 nanofarad. All right. So now that we have all this figured out, we have all of our passive components put onto our chip. And so the next thing we need to do is actually have our communication out. Because now our chip is getting power, it's getting ground, but now it needs to actually communicate. How is it going to talk back to the microcontroller to know how far it's turned? So there's a couple more things, and that's going to be our SCL and SDA pins. So these are I2C lines, which is a form of digital communication. And I'm just going to go ahead and choose a wire and just kind of make lines that are just kind of coming out like that right now. I'm doing nothing else other than that. These will later on be connected. However, just to note, I'm putting them out like that. Then there's a couple pins that need to be pulled to ground. So you can spend the time and go through the data sheet, read it, figure out what pins you need, what pins you don't need, and connect them as so. But to save us time, I know which pins need to be connected to ground. So I'm going to go and create a ground symbol here, put it right there. And there's 3 pins. Clock in needs to be connected to ground. 80 needs to be connected to ground. That's the address of the specific chip. And F sync needs to be pulled to ground, I believe. So these 3 things are now being pulled to ground. And below it, you can see all these things that say NC, 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 NC. We're like, well, what are those? What are those pins doing? That means no connect. You don't have to worry about them. Don't connect them. Simple as that. They're put there just because they are on the actual thing, but half of these pins don't even do anything. They're no connects. So that's what all those there are. All right. So, let me just make sure I'm not forgetting anything. Okay, nope. All right. I2C is a form of communication that is, if you remember in your logic class, like 201, you have your highs and your lows, so your zeros and ones. For I2C to work, it pulls the pin low, so it pulls it from a high state to a low state. Thus, if we want to actually use it to communicate, we need to have it being pulled high or pulled to a higher voltage before it gets pulled down with the communication. So we're going to use some pull up resistors. You might have heard that name before, pull up and pull down resistors in your 201 class. But I'm going to go to components again, and I'm going to choose Phil's lab library. And then I'm going to look up res for resistor. And now the same exact thing goes with our capacitors. Here's all of our different sizes of resistors. 0201 is the grain of sand thing that you see on there. And then 1206 is the bigger one at the top. Again, I'm going to use 0603s just because it's going to make it a little bit easier to put it on our board later on. And I'm just going to drag one of them out and put one there. I'm just going to copy it and paste it, and I'm doing just Control C and Control V to copy and paste, or you can click it and manually do it there. All right, so I'm going to extend these out a tiny bit. And then I'm going to connect one to SCL. So one is going to be connected to SCL, and the other one is going to be connected to SDA. So you could see that if the little circle is there, that means it's connected. If there's no circle and they're just going over like that, then they're not connected. So again, for I squared C to work, they need to be pulled high to a higher voltage. So I'm going to use this same voltage block down here and just Control C to copy it and Control V to paste it. And then I'll give you guys a second to catch up here. Yes, I'll go name them in the meantime. Again, if you want to name your component, you can double click it, which will open up the properties tab, and you can just go, in my opinion, we want it to be pulled high, so we want it to be a sort of high resistance. In the past, I've used just like 2.2K is a very good value for 3.3 volts. So I'm just going to do 2.2K ohm resistor. And so we have two 2.2K ohm resistors holding these pins high. All right. So now we have our kind of everything that we need to connect to actually power our board and communicate to another board. However, we're going to need something to, I'm just moving it off to the side. We're going to need something to actually connect it to. So if we want to connect it to a Arduino or another microcontroller, a Raspberry Pi, whatever you want, you need to be able to have some sort of connection. So if you go down to the components again, we're going to also use another component from Phil's lab called, it's a JST connector. You might have heard that before. If not, that's completely fine. But I'm just going to go drag and drop it out. But again, I went to components in Phil's lab portion and looked up JST. And this is a 6-pin connector. So we're going to have 6 pins that it could connect. And just to visualize what this connector looks like, I'm just going to double click it. And down here, I'm going to look at the 2D model. So you can kind of see there, it's a little like plastic connector that you can clip in. Those are JST connectors are super common and super useful for smaller electronics. This particular one has 6 pins, but you can have ones that have more pins or less pins or bigger, like a bigger connector or a smaller connector. There's a whole variety of different JST connectors that we can use. So once we have placed that component, I'm going to go ahead and mirror it just because I don't like how the pins are pointed the other direction. I'm going to double click this and scroll down to the bottom and click mirror. So again, I double clicked it to open up the properties tab, scrolled down to the bottom, and there it is. In the graphical section, you can see a little checkbox that says mirrored, and this will mirror it. So now the pins are faced the correct direction. All right. So I'm going to go back a little bit to teach you guys about net labels. Net labels, first of all, what's a net? What is, what does that mean? A net in this case is going to be what the wire is connected to. So for example, I'm going to go ahead and double click this wire and you can see that its net name is net C, question mark _2. You're like, what the hell does that mean? Or, this is kind of confusing and hard to follow. Once you do get to the stage of putting it on a PCB and you're trying to find your nets, that one's named 3.3 volts because it's connected to the 3.3 volts. So it knows it's connected to the 3.3 volt net, just like this one right here is connected to the 3.3 volt net. So all those things are now connected to each other. However, to make it easy to understand what is what later on, we're going to use something called net labels. So if you right click where the wire is at the top, you'll see a drop down that has wire, bus entry, and net label. We're going to go and click net label, which will bring this little guy up. And I'm going to go ahead and place it on the net that we just clicked on. So remember before it was named like net C _2, which is kind of hard to follow. However, this is connected to the C out pin of the IMU sensor. And so I'm going to go ahead and double click the net label. Oh, whoops. Double click the net label and just change the name to C out. So now I know that this is connected to the C out pin. That way I don't have to go back and see which is net C question mark 2 underscore. It doesn't make sense. So that one's connected to the C out. This is also a weird net name. So I'm going to change the one right here to, I'm just going to call it reg out. So that's just another pin right there. That's the reg out, the C out, and then those are all connected to ground. And then we want these ones to be SCL and SCA. So I'm going to click the net label again, and I'm going to just click it wherever. It doesn't matter exactly where you choose it on the line. Anywhere you click, it will work. So for example, as long as you're on the wire, you can see that little red X right there, meaning that you've selected that specific net. And you can click it there, it doesn't really matter. As long as the net label is connected to the net that you're trying to change the name of. So I'm going to just choose it right there. You can see the little red X indicating I'm changing this net. And up here, it's just going to be SCL. And right here is SDA. So now we have all of our nets labeled over here. We can now connect them anywhere without a physical wire. So, for example, if we want to connect it to this connector over here, I'm going to go ahead and create some wires. So we use 2 and 4. And I can go ahead and click the net label again. So again, I just did Control W to choose a wire. That way I didn't have to go up here and right click and change it to wire. Then I'm going to click the net labels and I'm going to choose 2 of them there. And then I can change this to SDA and this to SCL. Now, those 2 things are connected to each other, even if there's not a physical wire there. If they're on the same net, they're connected. So as long as the name is the same, then it's all good. They're connected. So the first pin right here, I'm going to make this one, go out a little bit. I'm going to make this one power. I'm going to choose 3 and 5 to be ground pins. And then 6, I'll show you what 6 is in a second. I kind of forgot to add it over there, but it is a interrupt pin. So, so I just added those 6 little lines right there. And this now is connected to the SDA pin, and this is connected to the SCL pin. Maybe I should flip those. No, I'll keep it the same for now. That's all right. Yeah.
Interrupt pins are usually output.
Yes. So interrupt pins are going to be an output from either this is going to be from this chip actually to interrupt it to stop it. I'm going to go ahead and add that right there. I forgot about it. Just Control W to create the wire. Put it out. Oops. What's happening? Oh. Where's my wire? Okay, there we go. I know what's happening. All right. And I'm going to go ahead and name this interrupt as well. So just int. And then I'm going to go back here and name this also an int. Oops. And then I'm going to connect the ground. I'm just going to place a ground symbol there and create connections between that one and this one. And the reason that I have a ground in between the SDA and SCL lines is because it's good practice to have a ground line in between a communication line when it comes to cables and things like that. So if you have multiple pins, it's a great idea to have a ground in between your data and your clock line in this case, but this communication pins, it just allows less noise interference and stuff like that. So having a ground in between those will allow a slightly less noise from when the wire is getting plugged in. Speaking of noise, we're going to go ahead and add a ferrite bead and two decoupling capacitors to the input power. So we know that this is the interrupt pin. These two are ground pins. There is our clock line for the data and our data line for the data, for the communication. And this is going to be our power right here. I'm just going to move this over a little bit. So again, I'm just dragging my mouse over and moving it over to the left. And we're going to add a ferrite bead. A ferrite bead is literally a piece of iron that kind of would surround your trace. And so it kind of goes in there and it's able to protect high frequency noise and stuff like that. So it filters out a lot of that high frequency noise from your signal. So you can imagine if your power line is noisy, your entire system is noisy because everything is based off of your power line. If you have a very smooth power line, then everything connected to that is also getting a smooth line. But if you have a super noisy power line, everything else can kind of get a little bit noisy and you can run into some issues with that. So it's good practice to put ferrite bead and decoupling capacitors after a connector because a lot of noise can come from wires just being in the air and stuff like that. Right now everyone's picking up 60 hertz from the wall even. If you touch yourself to an oscilloscope, you might see a little sine wave because your body is acting as antenna and it's actually able to pick that up. So wires do the same thing. There's tons of noise happening all over the room between our phones communicating, power in the walls, everything, noise is everywhere, and we want to filter that out. So in the components, again, we're using Phil's lab stuff. Shout out Phil's lab. I'm going to do FB for ferrite bead. And again, we have the same sizes. Remember, we had the 0805, 0603, or 0402. And you could see on the PCB how big each one of on the PCB ruler that DigiKey provided. Shout out DigiKey. You can see how big those actually are. So I'm just going to stick with 0603 just because that's what we've been using thus far. And I'm going to go ahead and place it right here. Whoops. There, place it right there. In addition to that, we're going to be using some decoupling capacitors. Decoupling capacitors do a very similar thing as ferrite bead. It just filters out a different type of frequency of noise. So we're going to have two capacitors on there. So I'm just going to look up cap again and put two decoupling capacitors just like that. I guess I can move them a bit down. Yeah, so now we have our ferrite bead and our two capacitors, and I'm going to connect these two capacitors to ground. And again, this will filter out a different frequency of noise than the ferrite bead, but the process is the same. It just it allows AC power to go straight to ground and allow DC power to act as like a open circuit right here. So any high frequency noise that is going from the input line will be just pulled to ground right here. And then the ferrite bead will filter out the rest.
What resistance at what frequency do you recommend for the ferrite bead?
Honestly, I just kind of go off either data sheets or other things that I see online. I don't personally go and do the calculations and everything like that. I just kind of have a general thing. For the ferrite bead, there's no real size that we're choosing here. It's just the actual footprint because the process is the same no matter what. But for the capacitors, I personally like to use 0.1 microfarads, but it's just kind of an arbitrary value. You can sit down and do the calculations to figure out what they're filtering exactly, but I know that usually those values will filter the frequencies that I'm trying to get rid of. All right, and then again, this is connected to power, so I'm just gonna copy one of the power symbols that we have there and place it there. All right. The last thing we need to do is just name these to 0.1 microfarads, the same we've been doing before. Whoops. 0.1 microfarads. And once you do that, our schematic is done. So I'm going to sit here for a second to let you guys catch up. Again, this is our input power line. So I'm actually forgot. I got to make a net label here. I'm going to say, I'm just going to call it 3, oops, plus 3V3 underscore in. That way I know that it is the power coming in and not the power in the rest of this thing. Yep. Oh yeah, I'm so sorry. I forgot. I was gonna make, oh geez, I forgot to do my spline. I was gonna make it bigger so everyone can completely forgot to do that. All right, that should be a little bit easier for you to see. I'm sorry, I completely forgot to do that before. You guys have been like using a telescope to see what I'm clicking up there. That's my bad. All right. So, all right. Just a kind of show of hands for the people that are following along, who is pretty much at this point. Cool. All right. I'm just gonna wait another 30 seconds, and then I'm gonna go ahead and move to the PCB.
Those wires extending out after the ceiling.
No, I can have them ending back anywhere. I just kind of like kind of that like that, but they could be end anywhere. I added them out so I can connect these resistors out here, but past that, it doesn't matter. All right. All right. It's good that I figured out to make my screen bigger by this point because I'm going to be going into the kind of stuff up here. So before we move on to our PCB, if you see, there's a bunch of little red squiggly lines there indicating that, something's might not be right. In addition to that, you might see that all these things are just C question mark, FB question mark, R question mark. You want to have designators for each one of those, except it could be an absolute pain if you're going to sit there and go through, if you have like 20 capacitors, click each one and name them individually. So Altium has a thing where it can automatically annotate your schematics. So if you go into design, oh wait, sorry, tools. If you go into tools, right here, there's going to be a thing that says annotation. Over here, there's a bunch of different options to annotate. The easiest one that will kind of automatically annotate them for you is the annotate schematics quietly. Don't really know why it's quiet, but it is. So that's the one we're going to be choosing. So again, if you go up to the top and go to Tools, Annotation, Annotate Schematics Quietly, go ahead and click that. And it's just going to let me know that some things are going to change. Now, boom, no more of the ugly red lines that you guys have been seeing this whole time. So now it's C1, C2, FB1, R1, R2, C6. Everything is labeled and it's a lot prettier now. So again, it's, go ahead. Yeah, it does pretty much. I think it goes left to right, top to bottom. So now that everything is nicely labeled for us, we could then, I'm just going to go ahead and save it. I'm going to do Control S to save it. And then now we can actually move into our PCB. So again, once you have added, in the beginning, we added our schematic and our PCB files. And when you save it for the first time, it's going to ask you to name it. You can name it whatever you want. I personally like to do a little SCH to indicate that it's the schematic. And then I named mine SCH MPU 6050. So when you save your schematic for the first time, things are going to pop up and it's say, okay, choose the name. I already saved it before this, so that wasn't there. But now I could go ahead and move to my PCB and you realize it's empty. Nothing's there. What's happening? I just did all that work. Altium made it a lot easier for you. So you could just go up to the top and click design and you can do import changes from the schematic. So again, once you're in the PCB document, you can go into design and import changes from the document. Oh, hold up. Let me save this. What's happening? Oh, okay. So I'm gonna go ahead and save this. I don't really know what was happening right there, but I'm just gonna call it PCB MPU 6050. Pretty sure I didn't need to do that before, but I just saved it right now, and now import changes. Okay, there we go. It's gonna pop up with this screen. So again, once you're in there and you save it, you go to design and import changes from schematic. And you're gonna see all these things that it's letting you know it's gonna do. First, you can validate these changes, and validating them shows that we got all these check marks, meaning we're good. It's gonna make these changes. Next, I can execute the changes, and now it gives more check marks, letting us know that everything is done. So I'm gonna give you guys a second there, but once you do get here, you just validate changes and then execute changes. And as long as everything is green, you're good. Now you can see all of your components are placed in here and they just place them outside the PCB way far away. You can just simply grab all of them and move them closer to the center. I am gonna move all of them kind of just whatever. It doesn't matter too much for right now. So this is your PCB editor. This is where you're going to spend the time actually creating your PCB. So there's a couple different editors in here. If you click 1 on your keyboard, you'll see the PCB kind of stack layer. If you click 2, you can see this form, which is kind of like a PCB traces and stuff like that. And if you click 3, you can see the 3D models. So those are the 3D models of the actual components. So 1, if you click 1 on your keyboard, this is where you can actually create your PCB size and platform. 2 is where you can make your traces and actually do your connections. And 3 is just a nice little visualizer so you can actually see what it looks like. So before we get started, I'm just going to create a board. Right now, the board is massive. That's just the automatic one that it comes in. So I'm going to press 1 on my keyboard and go up to design. So when you press 1 on your keyboard, it'll look like this. You'll have a green PCB in the background and all your components are grayed out. So when you press 1, you can go into this layer and then go into design. And I'm just going to redefine the board shape. So press 1, go to design, redefine board shape. Now I can create a new board shape here so you can see the cross is happening. Before I do that, I'm going to make it a little bit easier for me to make a symmetrical board. So if you press G on your keyboard, you can see all this comes up. This is your grid snap settings. So for example, if I choose a massive grid snap setting, you can see that like as I move in, like this is my circle, I can't be any more precise than that. But if I press G and go to 1, I can get a little bit more precision all the way to like, this is almost fluid. So if I want to make a PCB that is like kind of more symmetrical, I'll choose the biggest one. And that way I'll be able to make the everything a little bit easier. So I'm just gonna create pretty arbitrary size right now because we can fully edit it later on. But I just clicked in the bottom right corner to be in the very bottom, and I'm just drag it out maybe that big, um, by that big, by that big. And then it's going to leave you here. And then to exit this, all you need to do is hit either enter or escape, or it's escape, sorry. You hit escape. And then now you redefine your board shape. So I'm going to do that one more time for you. If you go into design, redefine board shape, you can just click there. And then if you want to change your grid snap settings, you can, whoops, you can press G, change your grid snap. If I choose mine to be the biggest when I'm creating my board, redefine board shape, boom, 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 and then hit escape. And here's my new board size. Much more reasonable compared to that big one that we were dealing with before. Right now, if you want, you can kind of smooth the edges so your PCB doesn't poke someone's eye out. They're very pokey in the corners. Just it looks nice when you make them a little bit rounder. Purely a preference thing. But in the design, you can also go edit board shape. And now you're in something that looks like this. So now instead of redefining the entire shape, you can kind of just make edits to it. And I'm just going to choose a corner right there and click it. And you'll notice that initially, okay, it won't look like that for you. Initially, it'll look like this. And you're like, oh, I don't want to do that. If while you're clicking and dragging, you press Shift Space on your keyboard, it'll give you options to change like this. So there's the round, there's the entire board, or there's kind of like more like this. So I want to do the round ones, and I'm just going to go down one snap. Again, I'm on the biggest snap grid setting, so I could just do one, and whoops, I could just do one on each corner. And again, you go to design, edit board shape, click and drag the corner, and then do shift space at the same time. And then I'm just gonna go one snap grid on each side. And then escape again. And then boom, I have a rounder PCB that to me looks a little bit nicer. I'll give you guys a second to catch up. And I know we're kind of running a little bit forward now. So I'm gonna try to wrap it up here. And then if you guys want, I'm gonna post a video that kind of goes over this exact the next steps to take if you want. However, we're probably gonna go over it next lecture as well. But once you get to this point, you can press 2 to move back to here. And now you're ready to place all your parts. So again, we're going to go ahead and finish this next week and actually start our PCB design portion of it. But yeah, that's what we're going to go. That's the today. All right, cool. Hey. Hey. All right. Also, if you guys want, if you go ahead and follow the videos and finish the PCB before next one, we got some merch, we got some shirts and fans and other stuff like that. If you finish everything before next lecture, you can go ahead and pick out some merch. We got these little, DigiKey fanny packs and fans and shirts and stuff like that. So if you want to go above and beyond and finish it before next time, you can get some free merch you can pick out of. Yeah. What's up, Henry? What's happening?
I kind of get lost. Yeah. So.
You saw that, right? So if you press one there, Then we'll go.